Hi everyone, this is Karen Hauk from UC Berkeley. Welcome to our Solar Week Live webinar featuring Dr. Yari Collado-Vega. She will talk today about space weather, the Sun-Earth connection. She'll talk for about 20 minutes and then answer your questions. Your microphone is muted and your webcam is off. However, you can ask a question in the Q&A box. Just move your pointer around and it will pop up. You can also, this week, for today and tomorrow, through the end of this week, ask questions of the solar scientists at solarweek.org. This webinar is being recorded. So welcome to Dr. Collado-Vega. She's originally from Ponce, Puerto Rico. She is a NASA scientist and is currently a space weather senior forecaster. She was one of the main scientists for the 2017 Total Solar Eclipse Education and Public Outreach event and a co-host of the NASA TV Live broadcast. She's been part of the NASA family for 14 years. Welcome.
Thank you so much, Karen. Hello, everybody. My name is Dr. Yari Collado-Vega, and like Karen said, I've been part of the NASA family for many years, 14 years, and I'm actually the space weather forecasting team lead here. And let me share my screen so you can see my presentation. So today I'm going to talk to you a little bit about space weather and the Sun-Earth connection. I work specifically for the Community Coordinating Modeling Center, CCMC, the Space Weather Laboratory here at Goddard Space Flight Center. I work for the Heliophysics Division, and Heliophysics right now has 5 labs. We have solar, heliospheric, geophysics, space weather, and then ITM lab. And this is part of the Space Weather Lab. So it's part of the whole conjunction of everything that we do here to study the heliophysics, which is a study of the environment in space that is dominated pretty much by the sun. So a little bit of where it all started. I'm actually from Ponce, Puerto Rico, like Karen said, and I come from, this beautiful island. One of the interesting stories about me is I always wanted to be a scientist. However, it wasn't until when I was a little girl that my parents, they united a lot of some money. I come from a very humble home, and money wasn't available for this kind of stuff. But they decided to take myself and my siblings to Orlando, Florida, because my sister was her 15th birthday, and we were all excited because we were going to Disney World. But one of the things my parents said is yeah, we're going to go to a place that you're going to like the best. And I said, which place is that? And they took me to the Kennedy Space Center, the visitor center, the visitor complex that they have there. And that just changed my life completely. That was the first time that I said that I wanted to work for NASA. I was 6 years old, and I just fell in love with anything that had to do with space, with exploration, and that's pretty much what all started. So I went to the University of Puerto Rico and did my bachelor's and my master's in physics there. While I was doing my bachelor's and my master's, I actually started working here at NASA. I applied many times. I didn't get in the first time, but one of those times I got in, and I was super excited. And I started in 2003 as an intern. And that's when I actually got included and got everything into what heliophysics was. And for me, it was something really, really exciting that I didn't know about. I didn't know that the sun could actually, cause all these problems to our technology. And, a little girl coming from this little island, for me, it was something completely new, and I fell in love with the field. So I started doing a co-op program, Goddard, which I had the opportunity to do, and I was a student and also a government employee here at Goddard. So I had to come every 6 months and work here. So every 6 months I had to move back and forth. So in Puerto Rico I would rent an apartment, and here I would rent an apartment. I would have to move my furniture or rent my furniture most of the time. So it was a lot of sacrifices, but it was totally worth it because here I am. When I finished my master's, I, then decided that I wanted to have a job here as a scientist. So I did my PhD in space physics. So I went to Catholic University of America in Washington, D.C., and I did my PhD in physics there, and I studied pretty much the instabilities around the Earth's magnetic field caused by the solar wind. So it was very interesting, and like you can see, there's definitely very different environments. You have a girl coming from a very warm place to the cold and the weather. The first time that I saw snow, I was like, I don't know, 24 years old. So it's very interesting to see a Puerto Rican girl trying to figure it out how to, drive in the snow or get all the ice out of the windshield from the car. But it's an interesting story. But enough about me. Now let's talk a little bit about the sun. So a lot of people, when you say imagine the sun, they imagine something very whimsical, very nice and calm. It's like a sunrise, something really relaxing. But as a scientist, this is pretty much what you see. And actually, the music is kind of intense. But as a scientist, you see the sun in many different views. The sun is actually very complex. It's not boring at all. And you can definitely see how in many different ways that we have to look at it. We have to analyze it. We have to study it to actually comprehend it as a whole. Not only that, when we study the sun, we also are trying to understand the stars in the universe. So it's a very interesting star that we have to look at every day. And I'm going to tell you a little bit more about why. The sun, has a very complex magnetic field. If you look at one of those areas in the sun where you have those very active regions, these are the regions where most of the solar flares, the coronal mass ejections originate from. And, you can see the magnetic field lines coming from one part to the other. But actually, you don't see the magnetic field lines, but you see the plasma, the particles following those magnetic field lines. And that's why you see all these beautiful loops on the surface of the sun when you actually look at those images from the sun that we have from the amazing images, the missions that we have outside in space. So this actually gives you an idea on how amazing this is, and we have to understand how these loops originate, what caused them to change the topology, so we can actually understand exactly what creates the solar flares or the coronal mass ejections, how everything gets accelerated. And we have now missions trying to understand this kind of capabilities. So the sun actually rotates, and it rotates differently in the equator than it does in the poles. And it's actually called differential rotation. And because of that, there's a lot of things that happen. A lot of complexity comes into when we talk about the magnetic field. And when we have a magnetic field model of the sun, is something that looks like this. This is actually showing to you the different active regions with those magnetic field lines that go from north to south. And also they're actually showing you on the poles, you have more magnetic field lines that are kind of open. And actually just, they're the ones that we have the fast solar wind coming in out of the sun, which is pretty much the corona expansion of the sun. So as a scientist, when we actually look at the sun, you actually look at the sun in different wavelengths. And you do that because you want to understand pretty much different temperatures. It's like an onion peel. You're peeling up the layers of the sun. So you see that sunspot right there. You're going from cooler to hotter temperatures, so the photosphere to the corona. And you can see how that sunspot, which is what you will look in the visible, actually looks now more intense, more bright, because now you're looking at it and the corona section, and it's actually what we call an active region. These are the regions where most of the flares actually originate from. Those are abrupt eruptions of radiation that cause a lot of radio communication problems here on Earth. So this is just to show you an idea on why we look at the sun on so many different wavelengths, all those amazing colors. And each color is just a different temperature. And here it's just a zoom in on that, and you can see the sunspot going there, and then you can see how it actually changes, and it's an amazing thing. Not only that, depending on the temperature that you're looking at, you see different features of the sun. You see coronal holes, which are actually parts of the sun. You have open magnetic field lines right there. There was one that look really dark, and these are areas where you have the open magnetic field lines that actually you have fast solar wind coming from those areas. So these are actually, coronal holes actually cause also a lot of problems geomagnetically at Earth, because you have the solar wind is always there, and I'm going to tell you that in the next few slides. But sometimes you have fast solar wind coming in that actually disrupt the system too. And that actually comes from the coronal holes. But this is just an amazing, this is actually from the Solar Dynamic Observatory, or SDO, which is actually the highest imager that we have, on the resolution that we have out there looking at the sun. It downloads so much data that it has its own ground station. It's an amazing mission that we use every day. And then here, I'm just going to show you a different wavelength. One of them, the ones that I was showing you before, is 193 angstrom. Here in this wavelength, you can actually see very well some of the intense flares coming from that active region right there on the southwest. And you can actually see those flares coming in. And actually, this is actually from September last year. And the sun has a cycle, an 11-year cycle, and we're actually approaching what is called the solar minimum. So the activity of the sun is a little bit lower from the active regions. And this is actually September last year. So this is just to show you that, sometimes you never know what's going to happen. You can have an active region evolving that actually causes a lot of these problems. This active region had more than 20 flares, and it had actually one of the highest classifications flare, actually the highest classification flare of the whole cycle, of this cycle. So it's an immense thing that this actually happened not so long ago. And this is just to show you how amazing and why we have to look at the sun every day. Now, SDO is amazing on showing you the sources of the things that happen, but you have to block the sun to be able to see whatever comes out of it. So you have coronal mass ejections. Those are big. They're different than the solar flares. Those are big explosions of particles coming out of the solar surface. So these are actually things that get out, and you can actually see when you have the eruption. You will be able to see the eruption from the Solar Dynamic Observatory. However, you cannot see it, how it's going, where it's traveling, unless you block the sun. This is actually an artificial eclipse. It's what we call a coronagraph. And this is from SOHO, the Solar Hemispheric Observatory. SOHO is actually at L1. Which is a point between the sun and the earth that is closer to the earth. And you can see how when you block the sun, you can actually see some of that corona that you can actually see how the coronal mass ejections, get out and how they travel. And I'm just putting the movie to run. This is actually from October 2003. It was called a Halloween storm because it happened around Halloween. And it was an immense, it was immensely, a lot of activity happened. And then you have this, that rainy stuff that you see out there, it's actually the high energetic particles that are accelerated by that coronal mass ejection and how they affect the detector. It's an amazing thing that you can see. And when you have this kind of activity, there's a lot that can happen to the technology of the missions out in space. Not only that, there are particles that we have to learn how to forecast if we want to have humans out there in space, because there's a lot of radiation involved with them. So this is just an artificial, like I said, artificial eclipse. So that's why a lot of scientists are actually very excited about eclipses, because sometimes, most of the times, the moon blocks the sun in almost in a perfect way that you can see parts of the corona that you cannot usually see when you do these artificial eclipses. So that's why total solar eclipses are very important for scientists, because these are the parts where most of the CMEs originate, and we want to understand what happens and how this, the CMEs start, how it actually evolves, and how it can actually accelerate this high energetic particles into the solar system. And then why we care? Well, there's something called space weather, and the solar wind is always there. You have the solar wind actually compresses one side of the magnetosphere and elongates the other. But we need to understand what's happening when this space weather actually gets into, a strong solar storm that can cause a lot of damages to the technology and to the Earth environment. So, for example, if we want to understand the magnetic field at the Earth, the magnetic field environment, the magnetic field of the Earth pretty much has like a dipole kind of thing. But however, the south magnetic pole is the north geographic pole. So it's the way that you see right there on the bar on the right. And however, because of the solar wind interaction, like I said, it has like a different shape because it compresses on the day side and then elongates on the night side. So it has like a teardrop shape kind of thing. The interaction of the solar wind on the day side is very important because it causes a lot of the transmission of the mass and the energy into the system. So it's a very important, aspect of the whole heliophysics and space weather to understand how the solar wind interacts with the Earth environment. And one of the things that we want to understand is, what happens when you have that kind of strong compression happening because, for example, a coronal mass ejection or CME. So these are models that we use to understand or have a similarity of what happens. So this is the magnetic field of the Earth right here. On the left, on the top side, you're actually looking at in the colors and density. And on the right is just a zoom in on the Earth, like on the Earth area. And that boundary that you see right there, right here, is actually the magnetopods. This is the boundary, the last boundary that separates the solar wind with the magnetosphere. And, sometimes when you have a strong compression, that boundary actually compresses a lot, like you can see at the bottom left. And then on the right bottom, you can see how that magnetopods actually got compressed really hard. And that dotted line that you see right there is just in synchronous orbit. This is where a lot of telecommunication satellites are. And these are satellites that are not supposed to be in the solar wind environment. And when this kind of compression happens, you have, those satellites in a different environment they're not supposed to be. And this is very important for operators. And it's something that we also study because we want to understand what happens with that interaction, what happens with that compression. And we need to understand where this boundary is. And we use the models to have an idea where it is, but we also need, observations and hopefully in the near future, an imager that will capture where this boundary is. This is just to show you, a visualization that it was actually done by a simulation on how the particles interact with the Earth environment. You have the solar wind coming in, like I said, all the time. Then you have a very, this is the CME arriving and how the particles get deflected because the magnetic field of the Earth is pretty much our shield. It shields us from those particles. But because of the interaction that happens, sometimes those particles can get into the system and they dump huge amounts of energy and mass into the system. So this is something really important to understand, and it's very interesting. One of the things that we use also for understanding space weather is we use models like we did before to understand the Earth's magnetic field, to understand when and where the CMEs are going to impact. So you have the sun right here on the center. And then you have Mercury, Venus, Earth, and then Mars. And then these are the stereo satellites, or stereo ahead and behind. These are satellites that actually have a heliocentric orbit, and they're actually looking at the sun in a different angle. Not a different angle, a different view. They're looking at the backside of the sun. So this is a model that actually has the solar wind. You see that rotation happening. That's the solar wind. And then we analyze the CME and we input it in the model. And then the model gives you an idea of when and where the CME is going to impact. And this is an event that happened in 2012. And you can see how big that event is that impacts pretty much everything from one of the stereo satellites, Mercury, Venus, Earth, and even Mars. So this is an event that actually is going out there. It's pretty big, it's pretty wide, and it's going to actually interact with a lot of the different planets and probably different missions that are out there. So as a NASA entity, we do take into account anything that happens. We don't have a backside of the sun because we actually want to analyze anything that is out there, any CME that gets ejected, because it can impact one of the missions, NASA missions that we have out there, and we want to make sure that they know that if anything happens, because it can actually affect the instruments of those missions. So talking about affecting instruments of those missions, we have a lot of space weather issues, and the most common ones is, technologies, communication problems that are caused by this kind of activity, especially solar flares. Radio communications are disrupted, GPS errors and blackouts. You can have, signal loss of the GPS, and GPS are used by for many things, not only for you to know exactly where you're going in your car, but also, you know, they're used in agriculture and credit card transactions. So having this capability makes it, you know, use a lot of the things that we use every day, but we don't, if we lose that capability, you know, it could be problematic. Launch delays, you know, have to make sure that space weather environment is good for a launch. Military communications, we work really closely with the military, so they can have the models pertaining on the forecasting, so they can have very good military communications. Not only that, the power grid disruptions and blackouts, those are really important. You know, the compression that happens, the geomagnetic disturbance can create what we call geomagnetically induced currents, or GICs, which are the ones that can cause problems in the power grids. And, you know, the biggest blackout that has been known out there since in 1989, and was in Canada. And, you know, the Quebec was without power for 9 hours, and it was because of a solar storm. So there's something that definitely can happen, and we're trying to create better models to do better space weather forecasting, and there's a lot that goes into this and a lot of research. For example, we want to understand what will happen. This is the Earth. This is a model that shows the Earth magnetic field and what would actually happen if you have a very strong event interacting with the Earth environment. This is what we call a Carrington-like event. Carrington was a scientist in 1859 that was looking at the sun, and he saw something really curious, and he actually drew it. And what happened was, you know, there were a couple of intense flares and CMEs, and then 18 hours after that, auroras were seen in very low latitudes, including Cuba and Puerto Rico. So you know, you're imagining seeing an aurora so you know, lower latitudes. That means that the disturbance was really, really strong. So this kind of activity is very important, because back then the technology was a telegraph, and telegraphers were being shocked by electricity, you know, the sparks going on in the system. Not only that, the fires were started because of the sparks. So understanding what would happen in the Earth's magnetic field environment would, you know, makes us understand how we can mitigate any problems that could happen because of this. And this is actually a simulation, you know, trying to see what would happen if something like this actually impacted the Earth environment. You can see the magnetic field on the Earth on the day side, which is the front side on the sun side, will actually pretty much be eroded, and you know, pretty much our shield in that side will be completely gone. So a lot of problems could happen on missions that will be on that side. Not only that, you know, a lot of radiation could also come to the surface. So there's a lot of things that we have to consider, and a lot of things that we have to study. This has not happened since 1859, but you know, a lot of questions that we get is like when this will happen, and you know, we don't know, because you know, it depends on the activity on the sun. So this kind of activity causes beautiful auroras, and this just show you a visualization, an animation on how a coronal mass ejection could actually interact with the Earth magnetic field. And you can see right there the eruption happening. You see the coronal mass ejection traveling through space, and then you can see it interacting with the Earth magnetic field. And there's something that happens that's called magnetic reconnection. Magnetic reconnection is a change in the topology of the magnetic field change, and then you transfer that magnetic energy into the particle. So you can see there's reconnection happened on the day side, reconnection happened on the night side. Then the particles traveling through along that magnetic field line actually get ejected back into the system, and they create what we call the auroras. I call the auroras the rainbow of space weather, but when the aurora happens, you know, there's definitely a lot of activity coming from the sun, and that means that the magnetic field is disturbed of the Earth. The magnetic field of the Earth is disturbed. This will show you amazing pictures from Alaska, from a sounding rocket mission that my colleagues here had, and just to show you how amazing it is to see. I've never seen an aurora in person, and this is part of my bucket list. But you know, we try to understand also the auroras and how they form, what are they made of, how they move, how they evolve, because you know, these are actually footprints of the solar wind environment and how it actually disturbed the magnetic field of the Earth. One of the things that I want to say is also we have tools, a lot of tools that are available out there on the web that can actually show you the space weather environment. One of the tools is ISWA, the Integrated Space Weather Analysis Tool. It's a really good tool. You open it up, that's the website right there, and you can see everything that has anything to do with space weather in one web page. You don't need 8 or 9 or 10 different web pages open. It has different products, or what we call signets, that you can actually pick and then put it into your platform and then save the layout. And when you go back to the layout, it's actually the same way you saved it, with the same signets in the same time. You can go back in time in the past, or you can have it almost in real time. So it's an amazing tool that we use a lot as a forecaster. We use it a lot. Not only that, we're trying to introduce it more into education now, because I think it's something very powerful. You can have images, you can have data sets, you can have models, anything that you need in the space weather environment. And you know, as a CCMC person member, it's good to show you that we have many models available in-house, that we, you know, have them available for the public to use. You can do a run-on request online, and then you use the results of the models for your scientific research. So it's an amazing thing between, you know, a bridge between those modeler developers and then the scientific community. And the models that we have right now, we have more than 80 active, and they cover all the way from the corona to the solar wind, the heliosphere, to the magnetosphere, and then the inside of the magnetosphere. So it's an amazing collection of models. And, you know, one of the things that we're very big on right now is on the metrics and validations of this kind of models. And, you know, it establishes, you know, we have a very strong communication with the model developers and us, and also, the, you know, we give them the feedback of the people that use those models. And, you know, one of the last slides, we talk about space weather, we talk about heliophysics, but we need to understand this environment, which is a huge volume of space. And we don't have that many missions out there. We have about 18. They, you know, it seems like a lot, but actually it's not a lot. You know, we're talking about a huge amount of space. And we use anything, you know, observations, models, to actually understand what's going on in the environment. And here's just show you, you know, the heliophysics fleet. Some of the missions are already out there. Most of them, some of them are just launched, like Parker Solar Probe. Parker is going to be very important because Parker is trying to understand how the corona is hotter than the surface of the sun, how it accelerates the solar wind, and then how the solar wind is accelerated, and also how the particles that I just showed you, the ones that, you know, those rainy particles in the SOHO detector, how those particles get accelerated. So it's going to be an amazing data set that we need to, you know, improve our models that we use for space weather forecasting. And that was just recently launched. And then we have all the things that are in implementation and going to be soon launched, like ICON. And then ICON is going to be, you know, measuring the changes in the ionosphere that are caused by the solar wind environment and, you know, the interaction with the Earth magnetic field. So that's the last slide. And, you know, thank you so much for your attention. And, you know, if you have any questions, just let me know.
Oh, thank you so much, Yari. I'm going to read some questions that come from the bulletin board. So maybe I'll just start with a few and see how much time we have. This question is, if there are no sunspots right now, why have there been huge auroras? I thought auroras were only seen if there was sunspot activity.
That is actually a great question, and it has to do with what I already spoken about, right? When we go to the solar cycle and we go to the solar minimum, we don't have that many sunspots or active regions, but we do have what we call the corona holes, and those are areas of the solar, you know, the corona that have open magnetic field lines, and you have fast solar wind coming from those areas. And the thing is that fast solar wind actually will create a geomagnetic storm and will actually cause an aurora. So it's not like, you know, it's solar minimum, we don't have anything to do. No, there's, you know, there's other features and things that happen that can cause geomagnetic disturbances, like the corona holds high-speed streams. So there's definitely something to watch out. And they also cause changes in the inside of the magnetosphere that accelerate electrons, and they can cause a lot of damage in the instruments.
Great. Here's a question in a totally different realm. When is the next full solar eclipse in the U.S., and do you plan to go to it? And if so, what will you do while you're there, and what equipment will you bring?
Wow, that's a long question. The next one is in 2024, if I'm correct, and I'm planning on being there. Yes, it's difficult to say if I will be there because there's still a few years to come, but I'm planning to be there. When we, NASA, the last eclipse, NASA had this huge campaign where a lot of things were used to look at the solar eclipse. They had missions outside in space looking at the eclipse. They have planes looking at the solar eclipse. They had even the Coast Guard was working with us to look at the total solar eclipse. They had balloons, so it was a huge campaign to actually look at the total solar eclipse. And like I said, eclipses are very important because they let us know parts of the corona that we don't usually see, and these are areas that are very important because this is where the CMEs, the coronal mass ejections, the solar flares originated from, and we need to understand those processes. And what better way to understand something than to view it? So these are very important. So I mean, it could be anything. I mean, NASA, like I said, had a huge campaign for the last one in 2017. So probably for next one, we'll have something, also good that we can actually analyze this total solar eclipse. I'm definitely planning to go because this one, I couldn't actually watch it. We were there in Charleston and we couldn't see it because a cloud came in and at the same moment that we were having totality, and we couldn't see it. So it was very sad, but I enjoyed the lowering of the temperature, the changing of the light, So, and then the people around you, it's amazing to feel that kind of like excitement about things like this. And so it was an amazing experience, but I still need to see a total solar eclipse.
Yeah, I was lucky I got to see it in Jackson, Wyoming, and as it got dark, all the sort of automatic lighting for nighttime came on in the houses around us, which was very cool.
Yeah, no, you can hear the animals and everything changing, and it was amazing. It was amazing, even though we couldn't see it by our own using the glasses, and then you can only take the glasses out when it's totality. That's the only time that you can take them off. We couldn't see it, but it was definitely an amazing experience.
That's the thing about our sun. You never know when you're going to get to see it. Here is a question about the ionosphere. It says, what is the unique role of the ionosphere in regards to the Sun-Earth system? Does it protect us?
It's a very interesting question. The ionosphere is pretty much the upper atmosphere. It's like the connection between the space and the Earth atmosphere. It's very important because if you have something in space, for example, sending a signal to the ground, it has to go through the ionosphere. And the ionosphere is where, all these atoms get ionized by the sun. And then, you have changes because of this solar flares, for example. You have changes that happen in the ionosphere. And because of those changes, these signals can, get what we call scintillated, and there's changes in the way the signal travels, and you can lose communications, and like I also said, lose GPS signal. So it's very important. It's a very important aspect to study because it's what we use nowadays, right? It's our connection between space and the ground, pretty much. And there's a lot of changes that happen. Not only that, when the atmosphere composition happens, the satellites orbiting in it can change a little bit its orbit, and that's something that we also study, which is what we call drag. So there's a lot of things going on now in the atmosphere, and actually it's a field that is increasing a lot in interest because, like I said, it's pretty much, I don't know, like a connection between the space and the ground.
I have a couple of more questions. One is about what would happen if the sun's magnetic field increased, and one is about from someone who wants to be a scientist, but also wants to have 4 kids and wonders if it's hard to have kids and go to lots of conferences and do all the things that scientists have to do. So I could read either of those questions or both.
Well, I have time for only one.
Okay. You want to pick one? Do you want to?
I can do the one with the kids.
Okay. That sounds good.
It's good to talk about this kind of stuff, you know.
Yeah.
I can definitely relate to this question. I'm a scientist, and I have a kid. I have a 5-year-old, just turned 5 2 days ago. 5-year-old baby. She's my baby. And I'm also a single parent. So it's difficult, but it's definitely doable. You're definitely capable of having your family, but sometimes you have difficulties finding that life and work balance. But it's definitely doable. It's just, hard work, because I tell everybody, when I go home, I don't sit down and calm and rest and relax. I have to play with her and have to pay her attention. And it's a different environment, but it's definitely doable, and it's definitely worth it. I mean, as a woman, I think we're definitely powerful enough to study a career in science or engineer or in technology, and also have our families. And it's definitely doable, and we definitely have the power and the capability of doing it. And just make it happen.
Great. Okay, I think we should thank you so much, Dr. Collado-Vega, and thank you all for coming. I hope people will be able to answer our short survey if we have a link somewhere. And then if you have more questions, please head on over to solarweek.org to ask your questions. You have the rest of today and tomorrow, and then Solar Week will come again next March. And thank you so much for this live webinar. We will put this on our YouTube page as soon as we get it processed, so people can watch it then.
Thank you so much for your attention.
Thank you. Sunny days.